I will go ahead and get started then. So, thank you all for coming to my defense today. I'm a little surprised to see the crowd. um, and thank you to all the committee members I see present as well. So, I recognize most of you, but I'll just briefly introduce myself. I've been a student here at Tech for 5 years now, and I've been working with Dr. McCoy for 4 years. I did my bachelor's in chemical engineering, and then I hope after today, maybe the next few weeks, I'll be officially a master's of materials engineering. And by the end of my defense, I hope I've shown you some of the main highlights of my research these last few years. There we go. Great. First, I of course want to thank all the students who have been among our groups and helped me with making samples, training me on equipment, or helping me conduct tests. And again, thank you to all the committee members for all of your input and suggestions these last few years in our weekly meetings. It really helped me get to this point, having to meet with you so often. And then lastly, my research was possible with DOE funding. Here's my slide outline and my goal by the end of today's talk. If I had to give my thesis a one-liner, I'd say it was to characterize and help extend the full potential of Diels-Alder polymers, bearing in mind their possibility of side reactions that I think until the last few years have gone underappreciated. I'll do this by introducing important terminology with covalent adaptable networks, the Diels-Alder chemistry, potential side reactions, gelation, and kinetics. And I'll also mention a few of the previous works that really inspired my thoughts and some of the experiments I planned during my research. I'll also describe the generic characterization of our own thermosets, how we studied the Maleimide self-reaction, as well as the kinetics. Diels-Alder thermosets fall into the broader family of covalent adaptable networks, which are dynamically responsive polymers that change their topology and properties significantly with a stimulus like heat, electromagnetic fields, and pH. Their general advantages include their high mechanical strength and chemical and scratch resistance, like a conventional thermoset with permanent bonding. But unlike a conventional thermoset, the cans have reverse processes, which become active at relatively mild temperatures, say from 100 to 200 C, at which you can reprocess these materials. And this dynamic equilibrium between the forward and reverse processes allows for the recyclability and for their intrinsic self-healing properties. But this equilibrium tends to make them weaker to a particular type of deformation called creep, where constant stress is applied to the material. And some of these chemistries are also not practical without a catalyst to boost the reaction rate, which when you recycle it enough times, it will have to be replenished. So specifically, the Diels-Alder reaction is a type of 4+2 double bond reaction between a diene, such as these furans, and these dienophiles, such as these malamides, which has the electron-rich 2 double bonds and 1 electron-deficient double bond. And these can produce cycloadducts of 2 forms. One is this kinetically favored endoadduct, and the other one is this thermodynamically favored exoadduct. The endoadduct usually breaks up and forms at lower temperatures compared to the exo. So talking about a specific temperature range at which these occur can be ambiguous, but in general, the forward reactions remain predominant below 100 C, and then the reverse reactions will become more active past 60 C. Some of the generally cited advantages with this chemistry are its mild reaction conditions. You just need heat to stimulate it. and the fact that it can occur with most of the materials that can do this reaction without any solvent or catalyst to boost it. Um, and then a few byproducts, which I've put in red because these side reactions become more significant at the temperatures where you can perform retro Diels-Alder. First, I want to be a little optimistic and discuss some of the more promising applications with these materials. So, in this top left set of images are some conventional fused filament fabrication resins. And then down here is a DA resin. And one of the major challenges I see in 3D printing that Diels-Alder materials avoid is this interlayer adhesion. In many cases, 3D printed materials are considerably weaker in the print direction because the adhesion isn't strong in that between the layers. And DA materials, on the other hand, can form homogeneous layers because of their forward and reverse reactions occurring simultaneously to form chemical bonds between the layers. In this middle set of images, the researchers constructed a conductor out of Diels-Alder material, and then they spliced it and then healed it with just heat and showed that the conductor was able to light up the LED again, which just goes to show how well these materials can heal. And then in this last set of images in the top right are shown some robotic grippers out of DA material. And so a few of the major challenges with bringing robotics into our everyday lives is having differential grip strength and the wear and tear of many jointed parts like these hands or grippers. And the differential grip strength is important so that the gripper can apply the right amount of pressure to pick up different soft or hard objects. And ideally, these need to have a long service life. These researchers were able to show that some DA chemistries are good candidates to help tackle both of those issues due to their soft and self-healing qualities. On the flip side, there's practical limitations to using these materials that have malamides. Likely side reactions include the malamide self-reaction, a reaction between amines and malamides, and furan dehydration of the adduct. Of course, the desired reaction is this furan and malamide reaction. In the next few slides, I'll discuss how reactions A and B can occur so significantly. And although I mentioned the dehydration reaction here, C, I don't think it would occur appreciably for most DA polymers. There's actually a lot of research interest to efficiently do the forward then dehydration reaction as a green alternative to many byproducts of petroleum chemicals. For the research I read related to that, typical conditions were a proton-rich solvent, catalyst at 200 Celsius or more, which are uncommon for most DA materials. So the malamide self-reaction can happen because they thermally initiate themselves to form free radicals at high enough temperature. Electron spin studies showed that this probably occurs either due to thermal homolysis of this carbon-carbon double bond here, or due to a donor-acceptor complex between two malamides. And this particular bismalamide that I'm showing here, I also used for many of my studies, and it kind of worked out favorably because this is a majority component in most neat malamide resins and DA materials that are studied industrially and academically. Then my last comment here is that sometimes free radical generation can be slow, but almost always the propagation is rapid. And I think some of my results today will attest to that fact. Another likely side reaction is this Michaels addition between malamides and amines. One of the most common ways of attaching furans onto a prepolymer backbone is through an example reaction like this. So this epoxy group will react with amines. And epoxy amine reactions tend to be high conversion, but some authors who used similar DA synthesis schemes used HNMR and found that the epoxy amine reaction was incomplete for their system, sometimes ranging from 80 to up to 95%. And then those free amines can react with malamides at temperatures as low as 75 C. So gelation criteria were really important for my analysis. So I'll make a few comments on this slide. It's the process where a single molecule comes to span the entire sample volume. And that's possible if one of the reagents has an average functionality greater than 2, so that enough chains become interconnected and form a 3D network. And this will change the resin from just viscous or liquid-like character to a material with viscoelastic or solid and liquid character. One of the major statistical arguments that describe the process is Flory-Stockmeier theory, which has the general assumptions listed here. The first one is that reactions only occur between two types of functional groups, and two, one crosslink won't influence another crosslink's ability to form. And then this is one equation of interest, or this is one form of the equation of interest that comes out from Flory and Stockmeier's analysis. It relates the critical conversion to form a gel to the average functionality and the molar stoichiometric ratio of your starting reagents. And then this is what, on this slide, this is what I think you should know about the kinetics before I show you my results. Generic rate law is like the one that I have shown at the top, where you have a rate constant K, which is just a function of, or it counts for the temperature dependence of the reaction rate, multiplied by a function of the concentration of reactive species. And the most commonly used form of the rate constant used to this day in most kinetic studies is the Arrhenius rate constant, or Arrhenius equation, which is described by a thermal activation barrier and a frequency factor A. But this should be emphasized as just an empirical model. And in fact, a better model, which you can use to directly relate with the reaction thermodynamics, is the Eyring-Polanyi rate constant, which is instead described by a Gibbs energy of activation, or the delta G double dagger. The enthalpy of activation is analogous to the activation energy, and the entropy of activation is analogous to the frequency factor. And then the Eyring rate constant also has a built-in temperature term and the Boltzmann and Planck's constants into it. Okay, and for polymers in particular, reaction rates become not just a function of the reaction timescale, but also the diffusion timescale for the reactants to get close enough for the reaction to occur. And in liquid state reactions, this only usually becomes apparent after you've reached really high conversions. But in polymers, you also have gelation and vitrification that can occur. Gelation, in a sense, will cage your reactants, and then they have to diffuse around in order to form a new bond. But all polymers will also eventually, or at low enough temperatures, can turn glassy or vitrify. And this is where individual chains or segments lose their translational motion, and that will freeze over any additional reactions that can occur. In the next two slides, I'll share a few articles I found inspirational to my work. One of these was by Roscoe and others who also studied the Maleimide self-reaction. They use FTIR and HNMR to confirm the increasing disappearance of Maleimide was in fact due to its self-reaction. But the way they also showed this was by taking a sample to high temperature either 120 or 150 C, isotherming for 3 hours, and then cooling down. So I included one of their plots here. I plotted G star, which is an overall indicator of the stiffness of the material against temperature. So if you follow along some of their results, so heating up, isotherming at 120 C, there's not much change. If you go up to 150 C, you see an order of magnitude increase in the material stiffness. So another study I wanted to mention was by Maglietto and others. They built these time temperature transformation diagrams for the first time for a Diels-Alder chemistry, which shows some interesting features due to both adducts. The utility of these diagrams is you're able to predict what state the thermoset exists in based on the time spent at a certain temperature, which also works with temperature ramps. To explain this a little bit, on the y-axis would be temperature and the x-axis time, and the dashed lines are the conversion. The Fourier-Stockmaier conversion is the red line shown. So for example, with this particular chemistry, if you isothermed at 45 C and tracked along, it would take about an hour in order for it to gel. And the key difference that I wanted to point out from a conventional thermoset is that at high temperature, the equilibrium conversion levels off. And even though they don't show it, the same thing would be true for the gel conversion. It would eventually be the equilibrium conversion. So with that introduction in mind, I'll explain to you how we synthesized our own Diels-Alder thermosets. We also use polyethyramines and then this furfuryl glycetyl ether with the epoxy group to do the epoxy-amine reaction. And that created a 4-arm furan and a 6-arm furan. And we also use jeffamine T403 to synthesize this flexible tris-maleimide compound, which is in contrast to the more common bis-maleimide compound, which if you just look at the chemical structure, you can imagine it's not going to have a lot of flexibility in that backbone with the phenyl rings. Okay, on this slide, I just wanted to briefly mention that we checked for hydrogens or amine hydrogens with H&MR, but we didn't find any significant amounts of the amine remaining. So this allowed us to focus in on the impacts of just the maleimide self-reaction. And so now I'll show you some generic thermal characterization I performed on the DA thermosets, and these have already been mostly cured. I used differential scanning calorimetry, or DSC, for this. In the plot, I have the heat capacity against temperature, and I've plotted the prepolymers, which are the first three, Fa4, Fa6, and tris-maleimide, and then the full Diels-Alder thermosets, Fa4 MPM in red, the Fa6 MPM in purple, and the Fa4 tris-maleimide in blue. And I'll first bring your attention to the step and heat capacity at low temperature, which is owing to the glass transition. And as you would kind of expect, the TG increases from the prepolymers to the full Diels-Alder thermosets from the cross-linking. In other words, it would take a higher temperature or more energy to make the polymer segments gain motion. And for the DA polymers at high temperatures, there are two endothermic peaks that occur because of the separate retro Diels-Alder reactions of the exo and endo adducts. And if you examine the peak size and the temperature range, you can kind of get an idea about the concentration differences or the reaction thermodynamics among the different Diels-Alder thermosets. Which, for example, if you look at Fa4 MPM and Fa6 MPM, they occur in the same temperature window, which was unsurprising because they have this same or identical chemistry, they just have a difference in structure. But the retro Diels-Alder peaks for the Fa4 tris maleimide compound are shifted or occur at later temperatures, which you could say is because they're more stable. You could argue that from either an entropic or enthalpic argument. I also performed dynamic rheometry characterization on the same materials. And in these plots on the left, I have plotted up G star overall stiffness, and on the right, 10 delta, or your ratio of loss to storage character. and this is against temperature. So if we start at low temperature, the materials are initially glassy and very stiff. They undergo a step change in their softness, going through the glass transition and become more rubbery. And then at high enough temperature, after enough RDA reactions occur, they completely degel and flow. And so just here, you can see that the DA polymers have a clear viscoelastic character compared to the pre-polymers down here, which show just viscous character. And now I'll be moving on to our results to study the Maleimide self-reaction. In this slide, I plotted up again G star against temperature. At high temperatures, the DA polymers are expectedly initially flowy, but after some time and at high enough temperatures, it became really apparent to us that some irreversible changes in stiffening has started to occur with these samples. And so we tried various strategies to minimize the Maleimide self-reaction. In the first strategy, we introduced a free radical inhibitor, like this hydroquinone molecule. So if, for example, you follow along the red curve, which is the Fa4 MPM, and then you follow the orange curve, which has the hydroquinone additive, we can see that it delayed the irreversible stiffening by several tens of degrees. For the second strategy, we synthesized the tris maleimide compound with a flexible backbone, which is shown by the blue curves and the first plot. And this also worked to reduce the impact from the side reaction. For a final and third strategy, we just tried to reduce the maleimide content in order to reduce the self-reaction. So go through these. The red curve is the 1-to-1 stoichiometric case. The dark green is the 0.8, medium green 0.6, and lime green 0.4. And I think to our surprise a little bit, changing the maleimide content doesn't really significantly reduce the impact from the side reaction, which we partially attributed to this kind of dynamic interplay between mobility from using less crosslinker and from how far the side reaction could go because of that increased mobility. Another way we looked at the maleimide self-reaction was to just isotherm at high temperature. So I picked 120 C plotted on the left and 150 C plotted on the right. So at 120 C, again, this is G star against time. At 120 C, the materials have already gelled, so they don't have as much mobility, for example, as the samples at 150 C, which show clear flowy behavior. But at 150 C, the materials show rapid stiffening after about 10 to 20 minutes, the neat materials. But with hydroquinone, that was delayed to about 30 minutes. What's interesting is at 120 C, even though the materials have already gelled, they gradually stiffen after a few hours, which is surprising since there's less mobility and there's fewer free maleimides. The last way I tried to study the maleimide self-reaction is through a DSC cycling procedure where I heated the Fa4 material up to 150 C, isothermed for 10 minutes, and then cooled down repeatedly. And I show the results for that in plot A with heat capacity against temperature. After about 30 cycles, the RDA peaks completely or almost completely disappear. And then another interesting observation is that the TG broadens out after a few cycles, and then it eventually disappears. In plot B, I show the same procedure, but using the hydroquinone additive. And you'll see there's a much more gradual disappearance of those retro Diels-Alder peaks. And in the final plot, I integrated the heat capacity to calculate the enthalpy from the RDA peaks. And this again shows that the sample with hydroquinone still forms more Diels-Alder bonds for the same amount of time spent at 150 C. Another important observation was that after about 40 minutes, there was still about 2/3 of the original RDA enthalpy. But if we go back to the last slide, at 40 minutes, the materials had significantly stiffened by that point. So what that combined evidence suggested to me is that the true homopolymerization of malamides doesn't occur for the first couple hours. And instead, what has probably happened is that these monomeric bis malamide molecules have made these small oligomeric structures, which have several malamide groups on them. And as that happens, the average functionality for the malamide increases, which pushes the critical gelation conversion down. And so I think at some of those last rheology results, these have actually undergone gelation and not formed a true malamide network or polymeric bismalamide. So I'll now move on to the forward kinetics section. For the kinetics analysis, I chose Fa4 as the material to study. And here I'm showing the isothermal rheology results at mild temperatures ranging from 30 to 50 C for various stoichiometric ratios of samples. In the plot, I put up G prime or the storage character and G double prime, the loss character, against time at the different temperatures and ratios. And in dynamic rheometry, one measure of the gel point is where the two intersect, or where tan delta equals 1. In rheometry, the only practical measure of conversion that's available is what is predicted at gelation. So say Flory-Stockmeyer theory. And in these tests, the temperature I've imposed, and then I'm measuring the time till gelation. And so that's how I went about the forward analysis. And as you can see in these tests, sorry, I didn't mention that. The loss character starts off mainly viscous at the beginning, since it's just a raw resin. And then once enough clusters and a network forms, the elastic character eventually overtakes the viscous character. And these are still temperatures where the forward reactions are predominant. So naturally, a higher temperature leads to faster gelation. And then I performed microcalorimetry on the same samples at the same temperatures. Here, I'll first bring your attention to the raw heat flow against time plot in the top left. We initially see net endothermic heat flow for the first 30 minutes or so because the instrument has to stabilize and initially samples take in heat to reach the testing temperature. But ultimately, though, I end up fitting the cumulative enthalpy on the right plot, which I've already corrected. So to do the corrections and fitting, I start off with the rate equation, assuming there's no reverse process. And then I solve it for the malamide concentration. And so even though we expect some initial endothermic heat flow, in the long run, the heat flow will be dominated by the exothermic forward reactions. And after solving those, you get this fitting equation shown here at the bottom, and alpha is just a convenience variable. The fitting coefficients to fit this are the enthalpy of reaction, the forward rate constant, and this time shift factor. And when I integrate this for the first time, I start off at the exothermic peak here in the raw heat flow, but I clearly shouldn't have zero reaction enthalpy for the first hour. So to figure out how much I need to shift these up, I decided I incremented the cumulative enthalpy very gradually until the predicted conversion at the gel time was close to the Flory-Stockmeier conversion. And then the other stopping criteria was that the time shift factor became close to zero. Once both of those criteria were met, I used the last iteration of the fitting equation to predict the early heat flow, which shows you the fully corrected plot here. And on this slide, I wanted to just show you an example of the combined results for the rheology and microcalorimetry. This sample, Fa4 NPM 0.8 30C, gels at 640 minutes. And in the plot, I'm showing the viscoelastic parameters on the left. So G prime in red, complex viscosity in blue, and the tan delta in black. And on the right side of the plot, I'm showing the enthalpy. So the raw, or the enthalpy after it's been shifted and corrected, and then the predicted enthalpy from the fitting equation, which is the H kinetic. And it's not until about 3/4 of the way to the gel time where the predicted enthalpy splits off from the measured enthalpy. And I interpreted this as diffusion restriction that comes with forming a gel. And then I also noticed, so to give you some idea about how I picked the fitting bounds on that fitting equation, I noticed that the complex viscosity remained linear up to a certain point. And so I took that as the max fitting time. And then I chose my minimum fitting bound as the intersection point where the G prime suddenly changes slopes, which is this purple circle here. So with the previous results now in mind, I was then able to fit the kinetic rate constants on Arrhenius plot like the one shown here. So I have the natural log of the rate constant plotted against inverse temperature. So I obtained a set of rate constants from the microcalorimetric data, but I can also calculate a set of rate constants from the gel time in Flory-Stockmeier theory using this equation. So I show the fits for both. I have the microcalorimetry in red, and I have the blue, or the aerometry gel times in blue. And the fits agreed better than I kind of would have expected by just plugging in the gel time because I would have thought the rate constants with the gel times would have been leaning more towards the diffusion regime. But I didn't really see that with the forward analysis here. But then again, I have fairly large confidence bounds on my fits, which is the dashed lines, which intersect for the two data sets. And now I'll be moving on to the retro kinetic analysis. In the next couple of slides, I'll show how I went about this one way and then a second method. But in this first method, I started off by ramping the same samples from the isothermal rheology up to a high temperature, as I show in this plot here on the right, where the complex viscosity is in the lighter colors and sits atop G prime in the darker colors. Both of those variables, G prime and eta star, have been used in other research to define a rheological conversion, but these are usually not tied to the absolute conversion of functional groups. One of the other difficulties in performing rheokinetics analysis is that both of these variables have a temperature and a conversion dependence. I chose to work with complex viscosity, and in the next few slides, my goal was to account for the temperature dependence on the complex viscosity, therefore making it only a function of the conversion, and then calculate the conversion and use the high temperatures to perform an equilibrium analysis, all in the end to calculate the reaction thermodynamics. And G prime might have provided similar results, but one problem is that where I would want to perform the equilibrium analysis, there's a lot of noise in G prime since it's degelled and the network's no longer present. And then at these temperatures too, RDA reactions relax stresses quickly. So G prime might not be as reliable without some additional correction. So this slide, I'm showing my procedure for converting the complex viscosity on the temperature ramps to a measure of the absolute conversion. I started off by relating the thermal conversion from the microcalorimetry data to the complex viscosity, producing this first set of curves in plot A, where I have complex viscosity against thermal conversion. And then to determine the temperature dependence, I ran a fast temperature ramp test on a just mixed sample of Fa4 mpm. For polymers that are above their glass transition and haven't yet gelled, the temperature dependence is usually described pretty well by a fit of log viscosity against inverse temperature, which I've shown as the blue line in plot B. And the raw viscosity is red. So afterwards, I scale the complex viscosity, accounting for that temperature change, or how much I would expect the viscosity to change with temperature. And that green line is showing how much it's been scaled to account for that temperature dependence. And then the last plot, I'm showing some example results of where I've taken the measured viscosity shown in red, and then I've scaled it to a reference temperature, which is either 30, 40, 50 C, where I did my isotherm tests. And then I match it to the conversion in the first plot. And what gave me some confidence that this worked out all right is that the conversion doesn't start to decrease until about 60 C, shown in black, where I would expect the retro Diels-Alder to start becoming active for the endo adduct. So after I've converted all the temperature ramp data of complex viscosity to conversion, I get the left plot A. And to me, it seemed like the conversion curves might roughly overlap each other. So I decided I'm going to make the argument that this is kind of like a quasi equilibrium, even though I'm ramping up in temperature. And what that allowed me to do is then plot the log rate or log equilibrium constant calculated from the conversion onto an inverse temperature plot. And from fitting a line there, you back out the enthalpy and entropy of reaction. Initially, though, the values I obtained for fitting a line here in this region, they were, to me, way too large for a typical Diels-Alder reaction. So I called them apparent viscous enthalpy and entropy. But I've also already measured the enthalpy of reaction from my earlier results. So I thought maybe might try just setting them equal to each other, the viscous and the reaction parameters, so that I could calculate the entropy of reaction from this equation. If I do that and I solve for it, I get a reasonable value, and then I can use this bottom equation to calculate the reverse kinetic parameters for the Diels-Alder reaction. And these were quite similar to values obtained from other kinetic studies. But truthfully, I still hadn't convinced myself that this previous procedure had accurately determined the reaction thermodynamics. So I took a second approach, and that was to conduct multi-wave tests. um, so I mentioned earlier the G prime, G double prime intersection point is just one way of measuring the gel point. A more exact way in dynamic rheometry is to measure at multiple frequencies and then find the frequency independence point from the phase angle. But rather than doing multiple tests, these multi-waveform tests overlay multiple strain profiles instead of the usual single profile. And during the test, the material response is broken up into separate frequencies. So with that testing method, my idea was this. It's easy to prepare samples with various ratios of starting reagent. And if you change that ratio, you can change the critical gelation conversion. And at some high temperature, the equilibrium conversion will be that gel conversion. So I ran multiple temperature ramp tests shown here in plot B using the multi-waveform technique. And you can roughly see where the frequency curves become frequency independent by following along this line. So I then calculated the equilibrium constant using Flory-Stockmaier conversion and plotted that against the degelation temperature like I've shown in plot B. And once I fit again a Van Hoff curve to this, I have the reaction thermodynamic parameters, which are in pretty good agreement with the values shown on the previous slide. So minus 40 roughly, and minus 100 for the enthalpy and entropy. So with that, I'll conclude this. I hope I've convinced you that the self-reaction for malamides can significantly change the behavior of many DA materials. And we found that this aromatic bismalamide that's so commonly used is particularly susceptible to producing irreversible changes in similar systems. I want to be clear with my kinetic analysis. I assumed one forward and one retro Diels-Alder reaction, but the reality is that there's actually two because of the separate endo and exo adducts having different reaction thermodynamics and kinetics. And if you were to have a complete kinetic description, it would have to reflect both of those adducts. So measuring retro Diels-Alder reaction rates directly is hard. So some studies, like I just showed you, measure the reaction thermodynamics instead, and then calculate the reverse parameters by using the forward parameters as well. The one downfall with this approach is that if you have poor estimates in your forward parameters, those are naturally going to propagate to your reverse kinetic parameters. And if I was to carry out my work further, I would consider trying different radical inhibitors and maybe concentrations. I would also try to maybe model the self-cross-linking gelation at high temperature for the first few hours. And I thought maybe you could do this by updating the initial malamide concentration term and making the average functionality a function of time. That's one thought I had. Another thing you could do to study this work further would be to try to study the reaction rates but fit the data using diffusion limited models, which I didn't do. And then I completed some preliminary work by attempting a global optimization fit of the DSC heat flow data in order to back out the kinetic parameters for both exo and endo adducts, which I'm showing in the plot here. the blue lines are the optimized heat flow, and the red points and lines are the measured points. But it still needs some improvement. So this could be something else that could be done in the future. Finally, I'll just mention quickly what papers we've produced related to our work and the manuscripts we still plan to produce related to the work I've shown you today. Last year, we finished a report on using photothermal nanofiller to heat up and use the RDA reactions. This last year, earlier this year, we finished a manuscript related to the impacts and strategies to minimize the self-reaction. And then I also hope to publish another manuscript related to the kinetics analysis I've shown you today. And then, depending on what the committee thinks, we might divide up the rest of the data into a couple other manuscripts that will be headed by other students in our labs. So that concludes my talk. Thank you all for coming.
So first, questions from the audience and or from the committee, but three general questions from the committee, and then we'll dismiss the audience, and the committee will grill them for a while. So, questions?
Also affirm the activation like energy forward reactions.
Me. So the activation energy that I got from the from the Arrhenius fitting was about 76. With the Eyring model, about 73.
You showed the table comparing those with the literature.
Yeah, I have that too. Okay, so yeah, this top line is my data. So, and then the other ones are example studies I've pulled from. So, to the enthalpy of reaction, I got about -40. Other studies have gone between like -30 to 60. For the enthalpy, I got about 100, -110. Other studies have gone between about maybe -90 to -150.
So really 27,900.
Yeah, I thought it was very strange as well. But no, it was legitimate. I double checked that.
But other values also pretty much offset to all the other literature. So maybe their method could be something different.
Yeah, I think this paper, they were studying the rheology, but they were also using an elastomer. So there's very few cross-linking sites.
So 4.1 is also pretty much offset.
Yeah, so their kinetic parameters were off by a lot too, or not off, but just a lot more smaller than you'd expect.
Okay, I just have one curious question. So, for when your stoichiometry is not 1, can you still use standards they call 1 to find your gel trend?
You can. So you can use it, but it might not be as accurate. So Winter and Chamden, they're known for having or showing the method of frequency independence. They found from their analysis on off stoichiometric samples that it tends to be shifted like later.
Did you use the same thing in your data?
I don't think I did. So actually, I did run a like kind of multi-waveform test on one of my off stoichiometric samples. So here, I'll bring it up. So I ran a multi-frequency test on one of the off-stoichiometric samples, the FA4 NPM 0.8. And so they roughly intersected at a phase angle of 45. So I took that as, okay, in my case, for my chemistry, tan delta equals 1 is still fine to use.
Well, Brandon, nice talk, nice lots of data, nice analysis. Can you revisit just the practical aspects of these things, man? And with respect to, you said your optimistic application of these,
Yeah, sure. So yeah, I think. Sure, go ahead.
Be the biggest roadblock to, or are they used? How often are they used now?
I think they're mainly an academic interest. There's definitely push to get these more into certain applications like the 3D printing, like or grippers, that kind of thing. One of the big pushes I see is the 3D printing because of their advantages. You can melt them and then melt them multiple times. They have the self-healing. That's another big research interest, is that they can heal large scratches or like big chunks of material. So that's something of interest.
But what's the roadblock? What's the major roadblock?
So the major roadblock is the Maleimide self-reaction, I would say, because ideally you want these materials to be recycled multiple times, or you could print them multiple times by taking them to the RDA temperatures. But as I hope I've shown today, that with that self-reaction of one of the main reagents, there's a practical limitation to how long you can use these materials.
And what is the gripping mechanism there in the right top side? No. How do they grip?
I'm not sure. Sorry.
What about the cost? Is that also an issue?
Can be. The aromatic bismaleimide we used, it's more expensive than, say, like, I don't know, for sure more than like polyethylene or other really cheap resins. But I guess it depends on your application. You might justify the cost that way. If I gave like a ballpark estimate, I'd say like $5 per gram of material for a lot of DA resins. Main chunk is the malamides.
$5 per gram or kilogram? What did you say?
Probably like $3 to $5 per gram. Yeah, gram was correct.
Oh,
yeah, that's something we ran into often.
that's cheap.
That's cheap.
Particularly when you're going to do the mechanical tests at the end of the day, samples that are big enough to just run chemical tests on to get away with random material itself. To make the dog on
Yeah, in DSC I need 10 milligrams and rheometry maybe 0.1 grams, so it works out fine that way.
So then for identification, do you know like what phase it is usually applied for? Like I don't know. I feel like I read somewhere like whether it is applicable for solid phase better than gas. I don't remember. So that's why I'm asking. Is there any limitation of identification?
I don't think there's like so much a limitation as that the values you'll calculate is going to depend on how your reaction rates are affected. So if you have phase transformation, you have diffusion limitation, or you have like solvent in there, that will definitely affect the parameters you end up calculating for your reaction rate and what values you get for this energy barrier. And so I think it's also like oftentimes these are not called just the Gibbs energy of activation, but the apparent Gibbs energy of activation. So I think that apparent is important.
I tell them about kappa, their the iron equation.
Oh, kappa here. This is called the transmission coefficient. It's usually just assumed 1. It's the probability that a reactant gets over the transition barrier. But in most cases, it's just assumed 1.
So for the Arrhenius equation, that tells you really tells you the probability of the two reactants reaching the energy level at the top. And so the assumption is that once they reach the top, they react and go down the other side, but they can also bounce back. So the more complex systems, polymers, or whatever, a significant fraction don't make it to the other side. They come up to the top and then go back. So the kappa is a correction for that,
Okay, take care of that. Okay.
which has a lot of physics buried into it, but it's just put it there.
Yeah, I think I read somewhere that for gas phase reaction, hydrogen equation may not be that important because
Because the kappa is 1.
yeah, but for solid phase reaction, it could be important. Like that could be a significant difference between ions and what you get from ions then. Anyway, that's something I thought I read somewhere. So I just wanted to make sure asking.
Still a lot of simulation work and trying to understand what that bounce back is.
Yeah.
Energy variation. Okay. Off topic. Any questions? If not, dismiss the audience. Thanks everybody for attending, and see you another round.